Hi, I'm Harrison Goldstein. I'm a PhD student working on property-based testing with Benjamin Pierce at the University of Pennsylvania. This virtual poster is part of the ICFP 2021 Student Research Competition. Over the next few minutes, I'll tell you about ungenerators, what they are, how they work, and why they're cool. At a high level, ungenerators are backward random generators. A generator turns a source of randomness into a test input, and an ungenerator operates in reverse, recovering the random choices that produce a given test. Ungenerators can produce feedback for a generator that can be used to optimize the generator's distribution and hopefully lead it to more interesting test cases. We can write generators and ungenerators simultaneously using bidirectional programming. The key to making this work is recognizing that generators are essentially parsers. They turn unstructured random choices into structured data. There are well-known ways to automatically derive pretty printers from parsers, and we rely on those same tricks to derive ungenerators from generators. Following prior work, we implement bidirectional generators in Haskell using monadic profunctors. The monad interface provides tools for generator composition, and the profunctor interface makes it possible to add annotations for the backward direction of the computation. Finally, we require a select operation, which makes a random choice in the forward direction and recovers a random choice in the backward direction. Here are a few case studies that show that ungenerators are expressive and useful. First, we show that bidirectional generators are expressive enough for real-world use cases by implementing a generator for well-typed System F programs. This is known to be a difficult task for random input generators. The implementation is quite straightforward, but there is a small amount of extra work that needs to be done to make the generator bidirectional. In the forward direction, the generator generates a type and then produces an expression of that type. This means that in the backward direction, we need to provide a way to recover the original type from a resulting expression. Luckily, the obvious solution actually works. We can give the ungenerator access to a type checker. Sure, this is a bit of extra work, but we think it's fair to assume that the type checker would already have existed. Next, we give a use case for ungenerators based on a paper called Inputs from Hell. The idea is to optimize random input generation by handpicking some examples and then asking a generator to produce more inputs like those examples. In theory, if the examples have some desirable property, the randomly generated input should as well. The paper shows that this works well in practice, but their algorithm only works when the input language can be generated by a context-free grammar. And unfortunately, that means there's no hope we could use this with a generator for well-typed System F terms, for example. This is where ungenerators come in. We can mimic the Inputs from Hell algorithm by ungenerating the hand-picked inputs to produce a distribution of choices, and then making choices according to that distribution. Finally, we dip our toes into the world of machine learning by re-implementing a tool called RLCheck in terms of generators and ungenerators. In this case, the major improvement is that ungenerators let us easily pre-train the machine learning model. Preliminary experiments show that this does improve the overall performance of the learner, and ultimately the performance of the property-based testing algorithm. Thanks for looking at my poster. If you have questions, feel free to reach out to me on Twitter, by email, or find me at ICFP.